Hello everyone, my name is Decay and currently I'm a software engineer at Bloomberg London. I'm very happy today to represent my colleagues including Shurit Karthik, Marcelo Smith-Laser and Nelat Mavidovic from University of Southern California. This paper is about using architecture decay as predictor of issue and change progress. Let's first start with the motivation of this research. As a software engineer, when we talk about software maintenance, we usually talk about explicit issues. And these issues usually are unwanted behavior, including wrong computation, slow performance, and sometimes they crash the system. And all of them have visible effects that we can see. However, that is just the tip of the iceberg. Underneath, usually this is affected by something we call smells, implicit smells. So smells are not, it doesn't have visible effect, but it creates vulnerable parts in the system and it impacts system maintainabilities. And you can imagine it look like a house with the facade looks okay, but on the back, its structure having a lot of problems, having ad hoc patches here and there. This phenomenon we call architecture decay. In summary, architecture decay is the consequences of bad design and bad programming practice during the development and refactoring. So why does architecture decay matters? Because these are technical debts and the developers have to pay off during maintenance. A lot of papers and research have pointed out evidence, also like empirical studies. With this empirical evidence, we are wondering whether we can use architecture decays in order to predict properties of the system. First, to what extent we can use architecture smells to predict two properties, issue proneness and change proneness of the system. These properties basically will show how vulnerable a part of the system is. There are few benefits come with that. First, if we can foresee the future of issue and change proneness, we can allocate more resources for maintenance of that part. We can estimate if we can reduce the issue and change proneness by removing some smell instances. And that will be a factor we can decide when and where we do refactoring the system. Here is a data pipeline we use to collect the data. So for each particular version, we will have a list of files in that version, and we have the list of features related to that. And in here, the features are whether that file has been affected by a smell or not. The output in this case, we have a list of issues and changes related to that file in that version. The goal that we have in here is to use the features to predict the output in here. The next step, we need to do clustering, labeling the data in different clusters that can be easy to predict. In order to do that, we look at the distribution of the data and we figure out that it's follow the heavy tail distributions. It means that there are a small number of issues that are associated with a large number of issues and changes. We decide to use Pareto principle in order to divide the label. And we apply it twice in order to have 3 labels that will have the engineers to have more precise predictions. The first 4% will be highly affected, the next 16% will be mediums, and the last 80% will be low. After we label the data, it will look like this. You can see that the issue proneness and change proneness in here now are represented by labels. The next step, we have to balance the data. We apply a technique and rebalance the data. So now each label will be 1/3 of the whole data set. You can take a look into our paper to get more detail about that. We use a very popular validation we call cross-validation to split the data into different folds and then test based on that. We apply different machine learning techniques to get the result models. We compare these machine learning techniques and choose the best one with the best results. To evaluate the accuracies, we use precision and recall. Here is the definition of precision and recall. the important caveat that we want to point out in here that because we have 3 labels, it means that the baseline in this case is not 50%, it is 33% for both precision and recalls. So after we have that data pipeline, we apply that into 10 open source software systems, including 466 versions, and we use 3 architecture recovery techniques. The detail of them can be found in our papers. Now let's move on to the first result about the issue promise precision. As you can see in here, different color represent the result different architecture recovery techniques, and with a baseline of 33.3% in here, across 10 systems, we have average precision is from 69 to 76%, compared to the baseline is 2 times better than a baseline. Another thing that we want to point out in here that the 2 techniques, ICSA and ARC, performs up to 15% better than PKG. So one conclusion in here is that the recovery technique plays an important role in order to have a better prediction capability. The same result is observed in recall. On average in here, we have the value from 67 to 75%, 2 times better than the baseline. And again in here, ICSA and ARC performs sometimes 30% better than PKG. For the change promise, we also have the same observations from the result. So on average, we can predict 2 times better than the baseline for both precision and recall. The conclusion for this result is that we can see that using the system history, we can accurately predict the issues and change promise of the system in the futures. However, one problem in here is that if the system have a short history, the result might not be correct. So that's why we define the next research question, whether the software system has some shared property regarding issue and change promise. If yes, it means that we can use the history of some system to build generic models, and then we can use that to predict the system with a short history. So here's how we do that. With a 10 subset system, we select one as a testing system and the rest as a training system. So here's an example of combination of other 9 systems with a 1 testing system. And the same thing, we feed it through machine learning to get the model and the result of this model. Let's look at the first result, the issue promise precision under the ICSA views. The baseline here is 33.3%. So the blue color represents the result in the first question. The orange color represents when we combine all the 10 systems and use K4 validation. And the gray one shows the result when we use 9 systems to build the training set and 1 system for the test set. So the first observation we can see in here that when we use all 10 systems, the precision is lesser when we use tenfold cross-validation within a single system. So that probably because when we add more systems, it creates more noise. So that's why the result cannot predict accurately for a single system. Look at the 9 other systems result. As you can see that it's less than 2 others. It's still very good, and in most of the time it's 1.5 times better than the baseline. We can conclude that if we don't have a long history, using 9 other systems could be good for the starting point to build the model. And when our system have a longer and longer history with more versions, we can start switching to include more of the data from that particular systems. The same result we can observe for the recall in the ICSA. There are a few more interesting observations. You can find that details in our paper. So in summary, our study is the first prediction study using architecture smells. There are 3 key findings we found. First, architecture smells have consistent impact on the issue and change promise. So it means that we can use the history of the system in order to predict the issue and change promise of the future versions. Second, Architecture smell-based model can be reused for the new software system with a short history, and over time we can include more data of that system to improve the accuracy of the model. And the last one, the recovery techniques play significant role to improve the model accuracies. Having said that, for the future work, we want to extend our work in 2 dimensions. Deeper, we want to analyze if we can combine different kind of smells under different architectural recovery techniques that can improve the accuracy of the predictions. Second, we want to compare whether affected by a single smell or multiple smell will cause more severe problem for the system. For broader study, we want to include new recovery techniques that can help us to identify new type smells. And we want to use architecture smells to develop new metrics that can be used to determine when we need to do architectural refactoring. Thank you for listening, and I'm very happy to answer any follow-up questions.